good morning, everyone. So thank you for all being here. Thank you for people online or still joining currently. So this is my great pleasure to welcome back Samy to give this talk here at Idiap after so many years elsewhere, right? So as usual, I need to do a short welcoming message. Okay. So for those of you who don't know Samy, so Professor Samy Bengio, right now, holds a PhD in computer science from the University of Montreal. Is now the senior director of machine learning research at Apple since 2021. And now he's adjunct professor at EPFL since the end of last year, right? Before that, he was at Google, so distinguished scientist at Google Research. He joined in 2007. Just before that, he was at Idiap. I don't know when you started, like
1999.
1999, exactly. So 1999, so nearly 10 years at Idiap.
Yes.
Yeah. And so he's well known for many pieces of work in machine learning, as you know, and deep learning. And also is one of the co-author of Torch, the well-known machine learning library that many of you are using a derivative from, right? So, and then Samy asked me not to speak about the rest because we are all here to hear about his presentation. So thank you, Samy, for coming, and the floor is yours.
Thanks, Sebastian. Thanks, everyone, for coming. Thanks for the kind invitation to give the talk. It's indeed a pleasure to be back at Idiap. I came back a few times in the last 18 years, but it's always nice to see that Idiap is doing well. Reminds me of many fond souvenirs, and I see a few people I still know, but actually most of you I don't. But I will have the opportunity to see you more. I will indeed come more often in Switzerland in the coming years, maybe a couple of times per year to say hello. We'll see how that goes. But let's move on to my talk. So how far can transformers reason? And this is a presentation that I gave actually at NeurIPS 2 months ago in December. This is joint work with Emmanuel Abbé, Aryo Lotfi, Colin Sandon, and Omid Sarami. They are both either at Apple with me or at EPFL. And for some of them, like Emmanuel, they are both at EPFL and Apple. So it's a joint work. I've been interested in reasoning for the past few years now. And it's mostly what I have time to do because the rest of my time I actually spend managing a large group of researchers and making sure that they can succeed. But reasoning is an interesting topic. So let's stop the presentation. Okay, let's try again. All right. Okay, so let's start by the basics. What do I mean by reasoning? This is not a word that we were using like 5-10 years ago. So it's kind of a recent terminology, and that came mostly with these very large models. Because when you think about it, these very large LLMs or other models, they are now able to do many things much better than we were able to do many years ago. But there are still a few things that are hard to do. And in particular, there's this class of problems that I call reasoning. And these problems are usually very hard, even for humans. And the only way to solve these very hard problems is to learn to decompose them into a sequence or a series of simpler problems. And so when you are able to do that, you can solve them, but you cannot solve them otherwise, most humans. And most machines, as we are going to see as well. So these are relevant in many places, but you will see them more often in problems like math or logic or algorithms that are more difficult than others. Planning. These are the kind of problems where It's not a simple problem. It's not like recognizing an image. It's a hard problem that you need to decompose into multiple steps. Why are these problems hard? Well, they have a few characteristics that make them harder. In particular, the input, what describes the problem, the context, the input, doesn't live in a low-dimensional space. Let me give you an example of what I mean that is easy compared to these problems. Language. Sequences of words happen, but they are actually very structured. Not any word can follow any other word. Most words follow words that are similar or that have a meaning because they are together. And so the actual, the embedding space of where words live is actually smaller than the number of words you can have or the number of combinations of words you can have. That looked hard apparently, but it's actually easier because there is a lot of structure in words. But you don't have that kind of structure in math. Most symbols can follow most other symbols, and there's no, if you had to compute the bigram or the number of times you see the sequence of 2 or 3 of these symbols, you won't learn a lot by seeing that. There's not a lot of statistical meaning to these sequences of symbols in math. So it's hard to represent because of that. The output also has something that is more difficult than language. In the output for language, once you've seen many words, you have a high likelihood of what's going to be the next one because of that structure. But again, in these math or logic problem, one change in the input has a dramatic change in the output as well. So it's not a smooth space a priori. And as I said, usually to solve them, you'll have to apply multiple steps of a reasoning problem, and it's not a single one-pass problem. There's this famous book about the system 1, system 2 type of problems, where system 1 is something that humans usually can solve in one go. You see an image, you recognize the face of your mother. That's system 1. That's very efficient in a few milliseconds or less. And then there's system 2, which are problems that are harder and that will take you time to actually solve. These are usually the reasoning problems. So let me give you an example of a problem that is apparently simple and is actually hard to solve with most big models. And this is an example here. So if I tell you that Marco is taller than Patricia, Bob is taller than Marco, Sarah is taller than Bob, Peter is taller than Sarah, and then I ask you, okay, is Marco taller than Sarah? So most humans can solve this because there's only 4 steps, but they won't solve it in one go like this. Oh, yes, sure, yes. They will have to, take a pen or go one step at a time and solve it. If you ask large models, here ChatGPT of 6 months ago, it will start by reasoning and give you like a summary of the question and how it would solve it. But at some point, it will make a mistake. One of the steps, you don't know which one, and it's always different. And it will not get it. And that's only with 4 things. Imagine if there was 10. And so these problems are apparently simple, but actually in practice, they are hard. You can actually, this kind of problem can happen in many other places. Here, it's an example with just math equivalences. So if you give a few equivalences of math, you know that if x is greater than 2, then x cubed is greater than 8. And you go on with a few of them, and then you ask, with these equivalences, can you get this other one? And the same thing will happen. It will try to give you like a long explanation about yes or no, but it will make a mistake at some point, and it's going to be wrong. But it will look very nice, but it's going to be wrong, sadly. Now, of course, as these models get bigger and bigger, and you hear about all of those great things that OpenAI or other big companies are doing, you will solve bigger and bigger problems, but you won't actually solve any problem. You will be limited by some limitations that these models have because of the hardness of these problems. So we can like step back and think about something that is even more abstract than anything I told you. And we can talk about this particular problem of syllogism which is if you know that A implies B and B implies C, you should be able to conclude that A implies C. So that's a very simple thing that we learn at school, and it's used in many other part of reasoning problems. You can represent these as graphs. I just draw small graphs here that says like A implies D, and then D implies F and E. Okay, so you can represent any of these problems with simple graphs like that. And then you can ask questions, okay, is there a path between A and E? And here, there is. But is there a path between A and G? And the answer is no. So you can see that seems easy when you see it, but it's actually a hard problem. Well, how can we test these kind of problems with our everyday LLMs? You can actually represent a graph using normal symbols, and here we use the greater than as a way to say an arrow. So J greater than B means that there's an arrow from J to B, which you see on the top right. And you can represent all the graph here. And then at the end, ask, is there a relation, is there a link between A and M? And so now we can look, and the answer here is yes. But if I was to ask between A and J, you would say no. That's the kind of problems we can represent. And the question is, well, is it hard? And if not, if it's easy, maybe, or if it's hard, does it depend on the number of edges, on the distance between nodes, on the, the total diameter of the problem? What makes it easy and hard? What are the features that you can think about? So we can, generate random graphs. Any random graph here with problems where there's at most a distance of 4 between the start and the end, the query and the target, and with at most 24 nodes. And if you generate random graphs and you train your model with that, you will actually get about 80% accuracy, which is, okay. It's a problem where 50% would be what you would get if it didn't understand. So you get something more than random. But did it actually learn the right thing? Did it understood the problem, or did it only picked up on some statistics about the problem? The side answer is that it only picked up on the statistics of the problem and not on the actual understanding of the problem. Because if I now generate some very specific type of graphs, and in that case, I generated what I call cycles. So cycles are graphs, and I'm going to talk about them, that have a very particular form, and we'll see why they're actually harder. But for these cycles, you get 50% accuracy. So it just did not understand how to solve these cycles, which are just one specific type of graphs. So it understands the random graphs. It doesn't understand some specific ones. Why are these ones hard to solve? Well, that's the topic of this presentation. Okay, so here is an example of cycles. On the left, there are 2 cycles. On the right, there's only 1 cycle. Both of them have the same number of nodes and the same number of edges, actually. They are just organized differently. On the left, you can see 2 circles or cycle, and there's no connection between the left and the right. And on the right, it's only 1 big cycle. And now I can always ask the same question. Is A connected to M? On the left, the answer is no. On the right, the answer is yes. So now I have reduced the generic problem of any graph to this particular type of graph. I will only show you 2 types of graphs. Here there's 6 nodes. We can take 8 nodes, 10 nodes, whatever, as many as you want. And we're going to check if we can train or fine-tune or whatever you want a model where you can see examples of that at training time or fine-tuning time, and then test them on new graphs of the same kind of structure at test time. Now, pay attention to the fact that the statistics of the left type of graph and the right type of graph are the same. So you cannot pick up on stats. They are the same. There's the same number of edges, the same number of nodes, etc. So that's not going to help you. So what happens when we try to train such models to solve such problems? It's harder. And actually, it gets harder as the size of the graph grows, as the number of edges and nodes grows. So what this experiment shows is that as the size of the graph, so n here, grows, you need more and more training examples to try to solve it, to get to some accuracy that is good enough. So, and the problem is that you see these curves, they're kind of exponential. So quickly, as n grows, you won't be able to solve it. And sure, you can, have a bigger model. We went from, it's still a few million, so it's kind of small with today's type of model. But these are exponential curves. So you won't solve anything big, because even if I was to multiply by 100 or 1,000 the size of the models, that exponential will only let you go to like 10 nodes, 12 nodes. You will never go to 100 nodes because it's an exponential curve. So that's a problem. All right, so what are we going to do with that? The first thing is trying to characterize why this problem is harder than others. Because maybe there are plenty of other problems like that, and we'd like to know. And maybe then the second step is we'd like to find a way to solve these kind of problems. So we started by defining a new measure, a new way to measure how hard a problem is. We called it the globality degree. So what is the globality degree? In essence, and no need to look at the equations, it's to understand how much of the input do you need at the same time in order to get a non-trivial answer at the end. So how much of all the input you have, you always need so that you can make a decision that is better than random. If I have time at the end, I'll give you an example that is more visual. If I show you an image of a cat and I cut the image into patches, how many patches do you need to say it's a cat? Actually, a very small number of them. Most of images of everyday life are not global. They are very local. You can get 10% of the image, 20% of the image, and you get it. But these graphs are not like that. You actually need most of the nodes. You need to understand most of the nodes at the same time to make a decision. It's one or two graphs, one or two cycles. So they are global. You need to see everything and at the same time make a decision. That's what makes it hard. So a few examples of these hard problems. There's this parity problem, or the k-parity problem, which is there are k k nodes or k inputs for which you care about the parity. The parity is whether there's an even or an odd number of the symbol that you care about. So the k-parity happens to be actually hard. It has a globality that is at least k, or n minus k, which is depending on how big k is. And the cycle task that I just described is actually the worst. It's n minus 1. So you actually need to see everything to be able to make a decision. Otherwise, you will only basically do a random guess. There are plenty of other measures that people have developed along the years to characterize how hard a problem is. And I give a list here. I won't go into details, but we had to define this new one specifically for transformers because most of the other ones were defined for other purposes, and their assumptions actually don't fit really what you can do with a transformer. So this one was more easy to understand and more aligned with what you do with a transformer usually, and these LLMs in particular. So we have a measure. That's good. What are we going to do? Well, the first thing is that we started with a conjecture that a task is going to be, you will be able to solve a problem as long as it have a small globality measure. So when you measure that globality, if it's small, you can solve it. If it's hard, you can't. Here I say constant. What I mean by constant is that it doesn't depend on n. It doesn't depend on the size of the input. If it depends on the size of the input, but as soon as the input grows, the globality measure grows as well, and you're basically doomed. You won't be able to solve hard problems. So that's a conjecture, but we actually also proved it in some cases. Here, it's not the one cycle against two cycle, it's once against three. It doesn't change anything. It was just easier to prove. It actually works for others, but the proof becomes more difficult to talk about. But I mean, the point is we can actually show that this measure actually represents the hardness of the problem, which is good news. We have a good measure. Bad news, because there are problems that are hard to solve, and that training a big transformer won't help you solve big problems, unfortunately. So what are we going to do? Where are we going next? Fortunately, there are techniques that already exist today that you can use if you use them appropriately. That will help us combat this globality problem. And you've heard of them, for most of you. They are called scratchpads or chain of thought, or depending on where you come from and how you use them. But these are the techniques that I'm going to talk about and how you can use them to actually solve this globality metric problem. So how can we break the globality barrier? Well, we're going to try to learn to decompose the problem. You remember at the beginning, I said, what is a reasoning problem? It's problems that are too hard to solve as is, but you can solve them if you can replace them by a sequence or a set of simpler problems such that you can solve each of them. And once you've solved one, it helps you solve the next one and the next one. And at the end, you've solved everything. So that's basically this illustration that I put here. You need to go up the mountain, but you are not going to go up just by jumping. You are going to start by solving one step, then a second step, then a third step, and at the end, you'll be there. So what I wrote at the top is, suppose you have some problem, and it's represented by the input x1 to xn, and you want to solve the problem, which is y, the final label. You will instead try to replace that problem by another one where you are going to add other intermediate labels in your problem, y1 to ym minus 1, and ym is your real problem, but you will add more stuff in the middle, and you will force them all to solve all of them in the right approach, in the right sequence. And when you do that, as we're going to show, you will be able to solve ym. Why? So in order to show that, we had to define something more, which we call the autoregressive globality. So remember, the globality is this measure that says how hard the problem is. The autoregressive globality now is we're going to compute the globality of each of the intermediate steps that we have. And if each of them is a small globality, then the final globality is also small. If any of them remains hard, you won't solve it. So now you have to think of how you can decompose your problem into sub-problems that, knowing the previous one, each one has a small globality or constant globality. If you do that, you will actually solve the problem, because the total globality will basically just be the max of all these globalities, or the sum. It's the same. It's the max. There are. I give an example here for the parity. If you have a problem, the parity problem, if instead of trying to give the parity of the input in one go, it's going to be hard. But if instead I give intermediate results, so I give the parity of one input, then the parity of two input, that includes the first one, then the parity of three inputs, that includes the first two, you can see that now every new parity problem only needs one more bit to decide left or right. So each of these small parity problem becomes easy to solve. And at the end, you actually solve the real parity problem. While if you had to go directly, the globality measure of the whole problem would be hard. So that's how you break that barrier, by decomposing into smaller problems that build on each other. I didn't say it at the beginning, but feel free to ask questions anytime. We don't need to wait, because if you wait, you may lose the understanding of the rest of the talk. Let me keep going. No. Yes. So how are we going now to use this idea for our cycles problem? We are just going to do like a search on the type of on the data we have. So for instance, if we have this problem on the left here, that is actually described here. You remember how we described that? Each greater than represents an arrow. So we give all of them, and then we ask a question: is A connected to M? Now in the output, instead of just asking yes or no, or 1 or 0, we are going to actually give it how to solve it. If you want to know whether it's yes or no, start with one edge, go to the next one, from that one, go to the next one, and if you come back to the first one, you know it's 2 cycles. If you don't, you know it's 1 cycle. And so every single of these steps is simple to solve, but the whole problem was hard to solve. So that's the example, and there's an example on the right, which does the same thing. So what happens now if you fine-tune your model with that kind of data? And of course, at test time, you don't give any hint. You just ask a question. It happens that indeed, suddenly, you can solve problems without any problems. So the blue curve is what we got in the first part of the talk. It's impossible to solve it unless you have an exponential number of training examples. And the orange one is when we actually use this new scratchpad or chain of thought approach. Suddenly, any size problem will work, and it's only going to grow. It will grow, but much less. And so you will solve much bigger problems thanks to this technique. But we're not done, because so far, all the examples I showed you was I fixed n, the size of the problem, so the number of nodes in the graph here. And at train time, I show you examples with size n. And at test time, I show you examples with size n. And that works well. But now we're going to play a game. And at train time, I show you cycles of 2 sizes, 6 and 18. So one of the graph has 6 a cycle of size 6, and the other one a cycle of size 18, or a cycle of size 24, of course. And at test time, it's going to be the same number of nodes, the same statistics, all of that, but now it's going to be 12 and 12. So nothing changed except that the size of the cycles are different. And when you try this technique, so the scratchpad technique that I just described, when you train on the first set and you test on the second one, where we change the statistics, so we are now out of distribution, unfortunately, it fails. As you can see in this graph here, you solve what I call the in-distribution. So all the examples that have the same statistics as in the test set and the train set, but it doesn't solve the out of distribution when you change the size. You didn't change the number of nodes, but you changed the size of the cycles within it. Then suddenly we're back to square one. Things are bad. But the talk continues, and so we can still do something. We can realize that the kind of scratchpad that we designed is actually very repetitive. What we do is, we tell it go to the next node, and then go to the next node and next node, and if this is the same as that, then it's 0, otherwise it's 1. But we always ask to go to the next node. So we can now try to design a repetitive and a recursive approach where you will only design one step, and it will learn to apply that step as many times as you need. And if you do that, the number of steps is not designed in the problem. You can solve any number of steps. So what we can realize is that in order to solve this problem, you actually don't need to see all the input. You just need to see the last node that you reached. Once you are in the last node that you reach, you can just look at the next one. So you can think of a state machine. You can forget about everything from the past that you've seen in the context. You only need the last state of your state machine to decide on what's the next state. So what we did was design a few new tokens in the LLM that have a meaning that say, don't look at things before that token and don't look at things after that token. Only look at this part of the input. So it's independent of the total size of the input. It only looks at one step that it needs to solve. And you just need to define that in your, in your LLM decoder. And when you do that, now you can actually solve any type of problem of any size. And indeed, we call that the inductive scratchpad. Could have been recursive scratchpad. But suddenly now you can solve them both in distribution and out of distribution much faster. So now we have an approach that can solve things with a much smaller type of models of any size, and it doesn't depend if the size is a new size that you've never seen at test time. So that's the summary of the first part. We designed this thing that we call the globality measure, or the globality degree, and the measure to measure it, which explains why some problems, which are the ones that we call reasoning problems, are hard to solve. And we explain why they are hard to solve, how to measure this, how it's aligned. And then we designed these new things that we call the inductive scratchpad, which when you use it appropriately, you can actually break that globality, and you can break it for problems of different statistics, so different number of nodes, etc. The only problem I would say is you still need to be able to design that scratchpad. So for each problem that you have to think, as a human, how would I solve that problem? How would I decompose that problem? And I can then show to the model examples of how to decompose that problem, and it will be able to apply this decomposition for any new problem. So it's not like we solved everything, because we had to tell it how to go from one step to the. So how to solve a problem was baked in examples of the training sets. It's not like we baked in the algorithm. We gave examples of how to solve it at train time, and then it solves it. So contrary to the normal machine learning approach where you give example of a solution, now you give an example of how to solve a problem. So it's like one level above. I think that's the main gist of this part. Yes?
So examples you gave decompose the chain of reasoning in a sequential way.
Yeah.
So you could have problems that are not sequential, where you need to compose over the disjunction or there's a more complex structure.
Yeah.
So are you suggesting the method? I mean, is that really one of the properties that your problem has to have for the method to work?
No. I think it would work if it's a set, but the inductive part where you design a state, if you're not able to design a state that actually represents everything in a short or a constant size, you won't be able to solve a bigger problem. You will be able to solve problems of the same size, because now in that case the fact that it's a chain or a set has no implication, but it has an implication for the inductive part where we were able to design a state machine that only needs the last state. And you can, for some set problems that you have, if the size of the sets that you need to solve the next step is small or constant at least and doesn't depend on n, then it's the same. You can. So no change. But again, you have to think a bit more. And there's another question.
You gave an example of a cycle at the part of the. It's a good question. You gave it. Thank you. You gave an example of a cycle as a part of inputs. Have you tried giving a different path or random path, or just basically as a part of the input, and see how that would work?
I mean, for random graphs, it's easy. So we know that the globality will actually be relatively low because it's random. And that's why at the beginning we were already able without any problem.
No, but for example, for the task of detecting a cycle in a graph, giving instead of a solution example of a cycle, giving an example of how to navigate within the graph. So basically, instead of going from A to B to A back,
Mhm.
going to A to B to C, just to show how to navigate in
Yeah,
general in the graph.
that's going to work as long as the length of the maximum length that you need to go over doesn't grow with n, which for a random graph will grow but very slowly. So it's not going to be a problem.
Thank you.
Yes, another question.
Yeah, thanks. I was just wondering, so what I'm understanding from the talk is that when you require to reason over large input, then it's problematic, but that somehow goes against the idea of transformers, which were designed to reason globally over all the inputs. So
Yeah.
I'm kind of starting to wonder, like, in our transformers right architecture, do we need something which is more local, like CNNs and so on, which do more hierarchical reasoning? So, yeah.
I think you won't solve it with any other similar type of CNNs or MLPs or record net. You will still have this problem. Actually, it's going to be worse for others because you will need a way to keep in a state, if it's a record net or in wherever machines you want to put it in, all the information of the input at the same time to be able to, and that's still going to be hard. That's not going to change, fortunately. Let me move on to the second part, which actually is going to be very similar to the first part, but it's going to be visual instead of graphs. So we thought, okay, can we have the equivalent of images, so image problems that are easy and image problems that are hard, and can we use the same type of techniques to distinguish them and then to solve them? So this is a joint work with a slightly different set of people. Aryo Lotfi, Enrico Fini, Moin Nabi, and Emmanuel Abbé. Both of them, again, all of them are either at Apple or at EPFL. And this is submitted. So let me give you some examples of visual tasks that are hard. Here, it's the equivalent of the parity problem. You remember, I told you it was hard when expressed as a text. It's also hard when expressed as visual. If I ask you, how many dots there is in the image, or not how many, but whether it's even or odd, it will actually be hard for reasons that we're going to see soon. There's this famous image from a book from 1969, written by Minsky and Papert. That book was kind of the first winter of machine learning or of neural nets. They wrote that book and they said there are problems that are hard to solve, and you won't solve it with a single layer neural network, which was what we were able to do by gradient descent back then. And that actually kind of killed the field for 15 years, but it came back. We're fine. But the funny part is that, yes, we were able to create models that are more nonlinear, multiple layers, like the MLP, and then everything else. But this particular task remained hard, and actually no one came back to that task. It was designed to say you need a nonlinear model. But if you take any nonlinear model today and you try to solve it, it's still going to be hard. For the same reason as we said at the beginning. And the reason is, like, if I ask you as a human, is there one or two circle here that are one into the other, or it's only one here or here, you will have a hard time. I actually can't say, unless you take a pen, and then with the pen you follow, and then you either you can see there's one or two graphs. Without the pen, you won't solve it. Well, the pen is the scratchpad. What do you do with that pen? You decompose the problem into simpler ones. You just, take an image, do one step of reasoning, take that image, do another step of reasoning. That's what you do with your pen. Without the pen, you don't solve it. Few other examples that are actually of the same category. Here there's like some number of nodes, and they are organized such that, again, there are actually one or two cycles. So it's the same idea of the one or two cycle, but it's visual and it's hard. When I showed them to you earlier in the talk, they looked very nice because they were separated. Now they are completely mingled, and it's very hard to solve in a visual way how to solve that. But if you take your pen and you color, you start from a node and you color everything you can reach with that node, now you can say, here there are 2 cycles. If you were to color everything blue, you would say there's only 1 cycle. Same here, it's not nodes, it's strings. So is there 1 or 2 strings? Or this one, which is fun as well, it's just a maze. Take any maze, put 2 dots in the maze and ask, are they connected or not? And no, I don't know for you, but if I just show you that, you will have a hard time just like telling me yes or no. But if I give you a pen, you'll find it easy, like any kid can solve that with a pen. You see, the pen, it's your solution. It's how you do reasoning. Without the pen, you're doomed. And I wanted to, so I think I told you at the beginning, to show you the difference between this kind of problem I just described and your normal vision task, which is there a cat in the image? Is this an image of my grandma? And in particular, you all know about ImageNet. So if you take ImageNet and you take all the images in ImageNet and you mask part of the images. So you mask 10% of the images, 20, 30, up to 90% of the image. And then you ask, is it a cat? Or anything you want to ask it. You will basically, for the ImageNet, performance will degrade, but not a lot. ImageNet is a very, very local task. The globality measure of ImageNet is very small. You can solve most problems with high accuracy with up to 90% of the image masked. You don't need it. But the cycles that I showed you in the previous slides, very quickly, you're doomed. So you will not solve them if I hide part of it. And that makes sense. If I hide, in the maze, if I hide the part where there's a wall that makes the 2 color disconnected, there's no way for you to know whether they're connected because the only information is in this wall. If I hide it, you're doomed. So that's why it's more global. All right, so what can we do? Well, I already told you how to solve that problem. Take a pen. But the idea of the pen, now you have to implement it in the right way. And the right way to implement it is to say, I'm going to tell you for training images how to solve it by give you intermediate solutions. I can color a few nodes. So I start from one place, and then I color up to 3 nodes. And then that's your new intermediate target. With that intermediate target, the next target is to color 3 more nodes, et cetera, et cetera. So you kind of handheld that the model so that it understands how to solve it. And suddenly, again, you transform a hard problem into a sequence of simpler one for the same reason we described in the first part. So this graph basically shows exactly what I already described. If you don't handheld, if you don't give like a scratchpad, that's the no scratchpad graph, and your accuracy will never lift up. It's going to be hard, even with a huge model. But if you now there's a very interesting thing. There's what we call the single frame. So I will only show you the final solution at training time. I will not show you intermediate values. I will show you, but still a very big hint. I will show you the image where part of it is blue and the rest is not blue. So it's the hint that says color it and you will find the solution. That's a huge hint. And if you do that, you can solve problems that are small up to large, but still you cannot solve big problems. So that hint, that single frame of telling you what to do, but just with 1 frame, helps you a lot, but at some point you fail. If now instead I designed this inductive scratchpad where it's more of a recurrent model and you can generate as many intermediate images as you want at train and at test time, then again we're back to the fact that now it works for any size and it's easy from the beginning. And there are multiple types of problems and they work the same. have time for questions on that part, or otherwise I have like 3 minutes to tell you another thing. And then we have plenty of other questions. So yes, I think we have time.
Slide on the previous slide, isn't the first graph is flipped? Like it's no, the next one.
Yes.
So the first graph, it should be 100% for small problem for the single frame scratchpad, but 50% for huge problem, isn't it? Or am I missing something? No, cycle 24 data set.
No, it's accuracy that we see. So
So
yeah.
accuracy should be
Yeah.
100% for small problem
Yeah.
and 50% for huge problem, isn't it? It's other way around for single frame scratchpad.
Yeah, I need to understand that. You're right.
What's accuracy?
Yes.
Model size.
Yeah, model size.
It's not the problem size. Okay, that's the problem.
Yes. So
Okay,
you need a
sorry.
bigger model to solve it.
Okay,
Yes,
you
you're
need a
right.
bigger model. Okay.
Okay.
I actually
There's
consider-
always
okay.
another way to see it.
Okay.
Where it works.
Yes, that's it's a reverse.
It's the a posteriori
Right.
thing. There's another question in the back.
Both tasks, you basically design the scratchpad.
Yes.
So my question is, what if we don't design it and this scratchpad being learned during training, let's say reinforcement learning or some reward function?
Good idea.
No,
What can I say?
no thoughts on that?
I mean, if you don't do anything, it's going to fail. You're doomed. Now you need the model to have a way to learn to do this, chain of thought or scratchpad. You can actually show them, which is what I told you in this presentation, but there are plenty of other ways to show it. And RL can be a way. And actually, we've seen recent models that are doing this kind of things where they generate, multiple chain of thought, and some of them are good and some of them are bad. And you tell the model, follow this one, not that one. So in a way, it's going to self-learn the same thing.
So
slower.
So let's say we define some states, intermediate states that we're going to train it with RL, and then my second question: how do you extend the definition of globality measure to that setup?
Because I think the measure doesn't change. It's the same. It's again the measure. If you are allowed to do a chain of thought, so you are allowed to have intermediate symbols. Like a chain of thought, then the globality measure is the max of each of the globality measure of each of them.
But we don't know the states. Okay, it is something that the model knows we don't know, so we cannot measure it.
Oh yeah, it's possible that you cannot measure it, but it still exists. You won't go around it, sadly.
Thank you.
Yeah, my question is somewhat related to what he asked. Would be using other reinforcement learning to learn the scratchpad one of the ways to
Definitely,
to work on the arc challenge, for instance, where like you have new problems popping up?
Mm-hmm. Yeah, I think so. Yes.
Okay.
I mean, there's plenty of open questions still about you will learn for some problems, will it generalize to other problems? But I think it's definitely one way to go.
Mm-hmm.
Yeah.
Okay.
I have a question about the stats on the tags that, as I read from the paper, that the state in the scratchpad are like made up from some tokens.
Yeah.
And this reminds me of a recent paper actually last month from Meta, that they use some continuous states as the part of the chain of thought.
Yes.
And they found and applied it to some similar graph in reasoning tasks that with like dozens of nodes and doing like such similar tasks. And they found that actually those tokens will those continuous embeddings will represent a BFS like a reasoning like a reasoning procedure similar to BFS.
Okay. Cool.
And I'm just curious about like what do you think in such inductive scratchpad, like what will happen if we like to similarly compress the states into some more continuous way?
I think it's possible that it would work. Yeah, I don't see any big problem. I mean, I haven't read enough of that paper to understand how the chain of thought appears by its own, or if it's handheld for training. But if it's handheld, I think it can appear in some hidden space if you force it to.
It can be
So
some
I
hidden
don't
space.
think,
Yeah,
I don't think it's a concern.
We have a comparable size of audience online. I wanted to give them a voice. So
Okay.
I pick up the first question from Claude. He's asking, what is the complexity of decomposing a problem into simpler ones? Isn't that decomposing requiring a reasoning model to be done, which cannot be inferred from data and statistics?
So in everything I showed in the presentation, I, the designer of the problems, knew how to decompose. So I actually taught the model by showing some training examples how to decompose. So that complexity that I knew, I don't count it because that's for training. At test time, it already knew how to solve it, and now you don't need to show it anything. It's going to decompose it appropriately. The real question is, if I show you a new problem that is far from anything you've seen at train time, and that needs to be decomposed to be solved, can you solve it? That's an open question.
And second and last question from the audience online is since we are trying to make a transformer simulate an automaton with different states, then why not directly use a state machine instead of a transformer?
Well, because you do want your model to be more versatile and be able to solve other problems than just this problem. Of course, you can, if you know that you will only have this problem, write some code and you're done. But this is not the purpose of machine learning, of course. You want to be able to solve problems that you've never seen, and maybe a variety of them, and generalize to setting that will be beyond the simple one-step recursion. So I think when it's possible, you're right, always go for the simple thing. Write the code if you can. Definitely. All right, I will change gear for the last part of the talk and talk about something rather different. It's still about reasoning, but it's a paper that a lot of people talked about, so I wanted to make sure that you also hear it from me. So it's called GSM symbolic, and it's again about reasoning. So this is another set of colleagues, Iman, Kevin, Human, Angel, and Mehrdad. They are all from Apple in that case. And that paper will be presented at iClear in a couple of months. All right, so I think I will actually go over, how long do I have here? Only a few minutes. I will directly go to the main point because I think all of that I've already described things. So there's this data set that people have been using for a couple of years now. It's called GSM 8K for grade school math questions, and there are 8,000 of them. And that's why it's called like that. And it's one of these benchmark data set that people use to say, oh, my LLM is better than yours. And this is the kind of examples that you see. So, Farmer Brown's farm is 200 acres, and Farmer Smith's farm is 100 acres, more than twice that. How many acres do the two farms have together? Okay, so it's very simple math. You need to do this formula, 2 times 200, blah, 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 and you get the solution. It's, most of us should solve that very easily. And indeed we do. And indeed, most LLMs do as well. So this is the kind of problems that you can solve. These models, you've heard these names, Gemma, Matstral, Phi, GPT, all these models. They solve this problem from 40% to up to 95%. So yeah, it's a done deal. We're done. What are we doing here? Well, not exactly. The question is, did we actually solve math problem, or did we just learn by heart these math problems? So here's what we did. We actually designed something a bit more generic. We took some of the test examples of GSM-8K. This is one example of them. This is the question, and this is the solution that you're expecting. And we templatized it. Every time there was the name of someone, a number, an object, we replaced it by a template. So for instance, we replaced a nephew by anything that is family oriented. We replaced 62 by some variable that we're going to call total. And then we add some math to say, well, this number can vary like this, and this number and this name can vary in that set, etc. And why did we do that? Because with this templatized version, we can generate as many examples as we want of the same problem. Now, here, if I gave you this problem and I replaced Sophie by Tom, would you make a mistake? Probably not. Even if I replace 62 by 64, would you make a mistake? Probably not, although there's more chance that you would. Well, the question was, are these LLMs going to make these mistakes, or did they actually understood how to do math? So we designed this experiment where for each of the test examples, we generated 50 copies of these examples by sampling in the distributions of what I just described. Now we have 50 different sets of the test set, and we looked at the result. Okay, so let me guide you to what we find. Let's take this model, Gemma 2, 9 billion parameters. This is the performance, 80 something, that is published. So people say, well, Gemma 2 is solving this problem 80%, 88% of the time. Great. This is what we get instead. So this is now it's a distribution because I have 50 copies of that test set. So I can compute the performance for each example, for each copy of the test set, and plot the distribution of that problem. And I see that the performance varies. So if I change a number, it changes the result, or a name, it changes the result. It's more or less good, and importantly, it's always worse than what they say. So, I mean, that's true for Gemma. It's not true for GPT-4o. GPT-4o is right on target. So when it said I had 95, we also found on average 95. Still on average, because in some cases it got 92 or 98. So there was some variations, even for the best models. But it stayed rather on target compared to Phi or Matstral or whatever. So that's kind of bothering. That if you change, apple for orange, you get a different answer. So, okay, did we understand anything? It's not what we're expecting from our reasoning machines. We did a few other things. We looked at how hard the problems were. You remember, Bob has 8 apples. He gave 2 to Peter and 3 to Mary. How many more apples did he have? Each of these clauses is a sentence. You can add one more sentence, or you can remove one sentence, and the problem becomes easier or harder, maybe. But if you really understand how to do math, adding 2 more apples or removing 2 shouldn't change that much. It does change. So for Gemma, for instance, you will see, how does it work? So yeah, M1 means one less clause, so it should be easier. And indeed, it is. And then P1 and P2 is, one more clause and 2 more clauses. So the fact that it's easier or harder it's debatable, but clearly it degrades with one or two more sentences, which means if it's able to reason, it's not able to reason very well, because as soon as you add one more thing to add or subtract, it fails more and more, and sometimes dramatically. Then we did another nasty trick. We added a distractor. We added a sentence that has no impact on the solution. So here, Oliver picks some kiwis and things happen to the kiwis, and you need to know how many remains. But we added that some of them were smaller than average. Have no impact on the number of kiwis, but we added that sentence with a particular number. Well, guess what? It didn't go well. This is the degradation, like 60% worse, up to 17% worse for one of the best models ever. So they all degrade if you tell them that some of the kiwis were smaller. All right. Kind of sad, but that's the conclusion. I'm done. Sorry. There are questions.
Right, run for questions. Sorry.
So I just wanted to know if you have checked if people also do worse about the kiwis.
So we didn't check formally. We did check with people in the team, and
well, people in the team might be a bias.
But but you're right. People also degrade. Yeah, definitely, people degrade, but not as dramatically as this.
Because there's a basic principle of
people
language
degrade
and
for some.
communication that
Yes, you want to use everything. I mean,
exactly,
clearly, my son makes that kind of mistake every day. So it happens for sure. But it doesn't degrade if I change apple for tomato. That never happens to none of us. It does degrade with the distractor. So humans want to use all the input, machines as well. We are currently doing more experiments about that and trying to, help the model, saying, be careful, there might be distractors. Just to give him a hint, but no results so far.
Hi. So just two questions. The first one is, what happens when, so here you just replace some variables, but what happens if you give some unwanted information in the problem? Say like some random text as some argumentation, but
that's the distractor. So half of the apples are smaller.
No, but something which is
like out of distribution. And the sun is yellow. That's what you're saying.
Yeah.
Something that has no
relevance.
We have not tested that.
And the second one is something on similar line. Like I think this goes very in a realm of uncertainty. So have you thought any measures to see how that distribution is varying with respect to the, I will not say noise, but kind of, the replacements?
I mean, yes, there should be some variance, of course, because you make all of us make mistakes sometimes, but it should be quite small and should be controlled and rare in a way. But it's okay that there is. It's a statistical machine, so it will have variance. The question is that an acceptable variance? And we think not. We think there's something bigger than just your random expected variance of because you have a generator and it generates some tokens. Yeah.
Thanks.
Any more?
Thank you very much for that. I want to ask, so did you have any control about the quality of the generated examples in the first setup? Because, of course, the answer doesn't change if oranges and the question is how many oranges. But if the question is like how many fruits, this will change, and basically then the training set is just.
We actually read all the questions. So we made sure that they all made sense, that they were all feasible. Yes.
It makes sense, but sorry, does it stay correct? Like, how sure are you that basically the example that's given now is?
So that's baked in we did verify this template. So if we wrote it correctly, this will always be true no matter what you put for X and Y, because we forced it to be true.
Okay.
So of course we may have done some mistake, but I don't think we did. That's code.
Okay, thank you.
So this is going to be more of a question on the previous section, sorry. So there's this idea that general reasoning requires some kind of abstraction generation and program synthesis, and so like this is an idea why that's discussed a lot. And do you think that your ideas of induction scratchpads could, in principle, teach an LLM to be able to do those sorts of things?
Yeah, but I mean, for now, what we've shown is in a controlled setting when there's only a small number of actions that you can take, you can learn to take them in the right order. I think as things get more complex, you will need to teach them the model more techniques to solve problems, and then. But I don't see any structural problem in doing so. But yeah.
Okay, thank you.
To be verified.
Okay.
Oh, by the way, you won't solve problems that you are not able to solve. So if there is no simple decomposition of the problem that you are aware of, it's possible that the model will not be able to solve it. You won't solve, truly exponential problems to solve. There's no way. There's no magic.
Sorry, just a quick question. You mentioned at some point that sum of small globalities is also a small globality, but does this condition always hold, or did I hear it wrong? Yeah, I think you said sum or a max of.
It's the max. Sorry.
It's the max. Okay,
Yeah.
I see.
It's just even the sum wouldn't do because it would depend on the number, but it's the max. Yeah.
Okay, I see. Okay, thank you.
It is actually a question more about the previous ones that it is really interesting to see that like the inductive scratchpad will get will be more effective than a fully educated one, as the inductive one it seems to be like one that have a narrower view of the previous history.
Yeah.
And it has been like somehow like a recurrent model or something like that. So I'm just curious about like what do you think if do you think like the recurrent models or like state space things will have a role in such reasoning tasks?
I mean, the reason why the inductive model works better than the fully informed model is that it will be able to solve problems of size or structure that it never saw before, because you actually decompose it into a step that will remain no matter how big the problem is.
Yeah.
So that's the main reason. And will that make it easier for, Mamba type of model, state space model? Yeah, maybe. I don't see. I think indeed state space model would have a harder time solving bigger and bigger problems because they need to summarize their thinking into the state, and the state is a finite size, so that's going to be hard. At least transformer keep a representation of each part of the input. State space model don't do that; they have to compress everything.
Yeah.
But with the inductive version, you have a hope to be able to solve it still.
Yeah. Right. Of course. Thank you.
It's not a question, it's more like a suggestion. Maybe you can save NVIDIA and do a DeepSeek evaluation and show it's worse than OpenAI, and then it will save the state of the US economy. Thank you.
What do you do with my stock in NVIDIA?
Exactly. Yeah. Stop manipulation right there. Yeah. LinkedIn post and that's it. Yeah.
You take the last one. Tego. Time is running.
Yeah. It's probably not a smart question, but is there anyone working on taking these problems here and try to convert to another type of problem that is easier to solve? For example, these problems like first order logic kind of problems that you can solve, for instance, with Prolog. Like, I don't know if somebody ever done that. Like, because if you encode this in a symbolic manner using Prolog, I mean, you can ask these questions and don't have this layer of uncertainty that you're having with it.
You would need your encoder to be good. So I think you might, in order to have a good encoder from one representation to the other, you may need to have some kind of scratchpad to be able to solve that to train that encoder.
So it follows in the same.
And so at some point you're going to be back to the problem. But it depends on some encoders might be easy to do, but I suspect your encoder will need to have a global view of the problem to be able to transform it into Prolog or anything.
Okay. Thank you.
All right, so thank you very much. Let's applaud the speaker and thanks Samy for coming.